Besides comparing the size of atoms, you can also compare the ionization energy of atoms. And this is the amount of energy it takes to remove an electron from an atom. And this process is always endothermic. So here's a rough graph showing ionization energy plotted versus atomic number. So we're moving across the n is equal to 3 row of the periodic table. From sodium to magnesium, sodium has 11 protons, magnesium has 12 protons, so it makes sense that it requires more energy to remove an electron from the 3s orbital when you have 12 positive protons compared to 11. And then notice you see a drop when we start filling out the 3p orbital. Even though aluminum has 13 protons, it's easier to remove its electron because we're taking it away from an orbital that exists farther from the nucleus on average, the 3p. When we go and keep adding one more electron, we're also increasing the number of protons. So in the 3p, it makes sense from aluminum to silicon to phosphorus, it increases. But then we notice sulfur has about the same value as phosphorus, even though sulfur has more protons in the nucleus. And then the trend continues with the increase. When we get to the end of the 3p, argon has the highest ionization energy in this row of the periodic table. We see a big drop when we go down to the 4s subshell. So a question, why is the value for sulfur about the same as the value for phosphorus? And when you look at the electron configurations, besides the atomic number changing, notice phosphorus has all unpaired electrons and sulfur's last electron is forced to pair up. So there is some repulsion that must make the ionization energy less than we expect because of the increased number of protons. That repulsion turns out to make it easier to remove the electron from the sulfur than it would have been had that electron existed in its own orbital. You can also take ionization energies one step at a time, so you can have a first ionization energy to form a cation. If you add energy to that cation, you'll separate an electron and you'll be left with the +2 cation, and so on. So every time you measure the ionization energy, you're always starting from the species that's made from the previous step. So for example, if you look at the data for magnesium, all ionization energies are positive. They're all increasing. It gets more and more difficult to remove an electron from something with a greater and greater positive charge. But the interesting thing to look for is, in this case, between the second and the third ionization energy, that this has a very large increase. Much larger than from 1 to 2, or from 3 to 4, or from 4 to 5. This is the biggest jump. And why is there such a big jump from ionization energy 2 to ionization energy 3? Well, if you look at the electron configuration of magnesium, we have a neon core and then 2 electrons in the 3s. So taking away the first electron would be from the 3s orbital. Taking away the second would also be from the 3s orbital. And remember, those are valence electrons. Once we get to removing the third electron, this 7,733 value, now we have to remove core electrons. So if you're given a series of data of the ionization energies, you want to look for a very large increase, and that'll tell you when you're shifting from valence electrons being removed to core electrons being removed. Electron affinity is the energy that's either absorbed or released when an electron is added to an atom. So instead of making cations, this time we're making anions. The energy release could either be positive or it could be negative. Most cases it'll be negative. But the reason that it could be either has to do with the fact that we have, besides having more attractions, with that extra electron is attracted to the nucleus, we also increase electron-electron repulsions. So here's another graph, and these electron affinities are all negative, so increasing is more stable on this graph. From magnesium to aluminum to silicon, we see a continuous increase, and then it drops down for phosphorus, increases for sulfur, increases for chlorine, and then drops way down for argon. Argon is fairly easy to understand because argon has a full p subshell. That's the 3p subshell is completely full. Argon does not readily accept another electron, so that electron doesn't want to go into an orbital, that'd be the 4s orbital. Chlorine has a very high electron affinity for the same reason. If chlorine gains one electron, chlorine with a -1 charge has the same number of electrons as the noble gas argon, so chlorine accepts an electron, turns into chloride, reaches the noble gas stability. Why does it drop from silicon down to phosphorus? Well, silicon has 2 electrons in the 3p, where phosphorus has a half-filled 3p. Adding another electron to silicon goes into an unoccupied p orbital, but for phosphorus to accept another electron, we have to increase that electron-electron repulsion again by putting an electron into a half-filled orbital.